Good morning everyone. My name is Prachi and today our topic for visually impaired students is chemistry of lanthanide elements. Lanthanides are the elements present in period 6 of the periodic table with atomic numbers 57 to 71. Since the last electron in the atoms of these elements enter the 4f orbital, therefore these elements constitute what is known as f block elements. These elements are also named as inner transition elements. This is because these elements constitute a transition series within the third transition series, more precisely the 5D transition series. These elements are located in the first row of the two rows of element kept at the base of the periodic table. The first element of the series is named lanthanum, that is equals to 57, and a group of 14 elements following lanthanum, which involves the gradual filling of 4f orbitals, is called the lanthanides. In other words, elements starting from cerium, Z is equals to 58, and ending with lutetium, Z is equals to 71, are known as lanthanides. The name lanthanides was wrongly coined as the ending IDE more correctly means a negative ion such as oxide or chloride ion. For a few years, IUPAC suggested a new name lanthanons instead of lanthanides to these elements. However, it was also disapproved soon because the ending on is preferred for non-metals, whereas the lanthanides are all typically metallic elements. IUPAC has finally approved these elements to be named as lanthanoids with the ending OID. These elements in the earlier years were called rare earth elements because of their occurrence in very small amounts. However, nowadays the term rare earth elements is itself misleading because many of these elements have been found to be abundantly available. For example, cerium Z is equals to 58 is as abundantly available as copper. Huge deposits of these elements have been located in USA, USSR, Scandinavia and India. Electronic structure and position of lanthanides in the periodic table. As already discussed, lanthanides involves the gradual filling of 4f orbitals. The ground state electronic configuration of each lanthanide is occupied by the outermost shell n is equals to 6 by the two 6s electrons. Since the energies of 6s, 5d and 4f are similar, the order of filling the 4f orbitals may show some irregularities. It is found that at lanthanum Z is equals to 57, the incoming electron enters the 5D subshell and therefore it has the following electronic configuration: La Z is equals to 57, XCF4, 4F0, 5D1, 6S2. However, as we moved onward after lanthanum, the energy of 4f subshell becomes distinctly lower than the 5d subshell. As a result, the next electron in cerium enters the 4f subshell. The electronic configuration of cerium is represented as Ce, Z is equals to 58, 54 Xe, 4f2, 5d0, 6s2. The filling of 4f subshell continues till one reaches ytterbium, which has the electronic configuration YB Z is equals to 70, 54 Xe, 4f14, 5d0, 6s2. F block elements may be defined as those elements in which the last electron enters the anti-penultimate energy level, that is n-2 subshell. Since both the 6s and 4f orbitals have been completely filled, the next electron has no choice but to go to the 5d orbital. In lutetium Z is equals to 71, the electron enters the 5d orbital and the electronic configuration is Lu Z is equals to 71, 54 Xe, 4f14, 5d1, 6s2. It is important to note that the electronic configuration of the penultimate shell n is equals to 5 is invariable as to p6 except for the three elements with lanthanum Z is equals to 57, gadolinium Z is equals to 64 and lutetium Z is equals to 71. It is equally important to note that the 4f orbitals are unoccupied in case of lanthanum Z is equals to 57. 4f orbitals are half filled in case of gadolinium Z is equals to 57 and 4f orbitals are completely filled in lutetium Z is equals to 71. General characteristics of lanthanides. The general electronic configuration of the lanthanides may be represented as lanthanides is equals to 54 Xe, 4f0 to 14, 5d021 6s2. The ground state electronic configuration of the outer shells of lanthanide atoms are given in table 4.1. Physical constants of lanthanides. Some of the important physical constants of lanthanides are given in table 4.2. Number 1. Ionization energies. Lanthanides have low ionization energies. The first ionization energies of the lanthanides increase in general but still shows some variation with atomic number across the lanthanide series. The trend is less clear for first ionization energy than for the sum of three ionizations. It is clear from the figure 4.1 the deviation are observed only for EU, GD and YBLU, which involves the half-filled and completely filled 4f orbitals. The first ionization energies of the lanthanides roughly corresponds to 550 kJ per mole, whereas the second ionization energies corresponds to 1150 kJ per mole. These values are comparable to calcium, which has the first and second ionization energies of the order of 590 kJ per mole and 1150 kJ per mole respectively. Number 2. Melting and boiling points. The melting point of any substance reflects the force of attraction between the atoms, molecules or ions that compose the solid. An inspection of the table 4.2 reveals that lanthanides possesses high melting and boiling points. However, the melting and especially the boiling points of lanthanides do not show any regular trend across the lanthanide series. The properties of lanthanides strongly suggest that 3 valence electrons per atom are involved in the metallic bond. The 4f electrons are not involved in metallic bonding as these are located on the individual atoms and are well shielded from each other. The most clear-cut anomalies in the lanthanides are provided by europium and ytterbium, which behave much as would be expected of divalent metals, indicating less than 3 electrons per atom involved in metallic bonding. These are also the two lanthanides which most readily from divalent ions in their compounds. In addition, these two ions have half-filled and completely filled 4f subshell respectively. This explains the low melting point in case of europium and ytterbium as compared to the values for the other lanthanide elements. Number 3. Density. The densities of the lanthanides do not display a regular trend across the lanthanide series. Both europium and ytterbium have usually low densities. Number 4. Heat of fusion and heat of vaporization. The amount of heat required to convert a substance from a solid at its melting point to a liquid is called heat of fusion, whereas the amount of heat required to convert a substance from a liquid at its boiling point to a gas is called the heat of vaporization. In both the cases, the energy required is used to overcome the attractive forces. In case of lanthanides, the heat of fusion and heat of vaporization do not show a regular trend across the lanthanide series. 5. Electronegativity value. Pauling defined electronegativity as the power of an atom in a molecule to attract electron toward itself. The lanthanides show the lower Pauling electronegativity value between 1 to 1.15. These values are very close to those of alkali metals and alkaline earth metals. Since the electronegativity values of lanthanides are almost same as that of s-block elements, it is anticipated that lanthanides form ionic compounds. Oxidation states. Oxidation state of +3 is shown by all these elements and in most cases is the most stable oxidation state. Some of the lanthanides in addition to +3 show +2 and +4 oxidation state as well. However, +2 and +4 oxidation states are always less stable than the +3 state. The reason for the unusual oxidation states of +2 and +4 can be attributed to the extra stability associated with F0, F7 and F14 electronic configurations. Examples giving various oxidation states are given below. Number 1. +3 oxidation states: La3 positive, Gd3 positive, Lu3 positive. Lanthanum, gadolinium, and lutetium distinctly display +3 oxidation state. This is because after the loss of 3 outermost electrons, these elements acquire the stable configuration of empty, half-filled, and completely filled 4f subshell as shown in table 4.3. Number 2. +4 oxidation states: C4 positive and Tb4 positive. The most stable oxidation state of cerium is +4. This is because after the loss of 4 electrons, Cerium acquires the outer electronic structure as F0, D0, S0, which corresponds to that of noble gas configuration. Ce Z is equals to 58. Ce4 positive 54Xc 4F0 5D0 6S0. Similarly, terbium acquires the half-filled F7 subshell configuration. Tb4 positive 54Xc 4F7. Number 3. Plus 2 oxidation state Eu and Yb. The most stable oxidation state of europium is plus 2. This is because after the loss of 2 electrons, europium acquires the outer electronic configuration of half-filled F7 subshell configuration. Similarly, terbium Z is equals to 70 acquires the outer electronic configuration of completely filled F14 subshell configuration. EUZ is equals to 63. EU2 positive 54Xc4F7. YBZ is equals to 70. YB2 positive 54Xc 4F14. The outer electronic configuration of various lanthanides in different oxidation states are given in table 4.3. There are instances which some of lanthanides display plus 2 and plus 4 oxidation states without acquiring either F0, F10 or F14 configuration. For example, samarium, thulium show plus 2 oxidation states with F6 and F13 electron respectively, which are 1 electron short of the required half-filled or completely filled configuration. Similarly, rhizodimium and neodymium show plus 4 oxidation states with F1 and F2 electronic configuration. The existence of such oxidation states, which cannot be explained on the basis of F0, F7 or F14 configuration, might be explained on the basis of other factors such as kinetic thermodynamic factors. Magnetic properties. The magnetic properties in chemical compounds determine the presence of paired or unpaired electrons. If substance containing only spin paired electrons are placed in the magnetic field, these are weakly repelled by the field. This phenomenon is called dimagnetium. On the other hand, substances containing one or more unpaired electrons, when placed in the magnetic field, are attracted by the magnetic field. This phenomenon is called paramagnetism. It is important to note that the attraction of each unpaired electron is many times stronger than the repulsion of all the spin paired electrons in that atom. Most of the lanthanides ion, with the exception of La3 positive, Lu3 positive, Ce4 positive and Yb2 positive ions, are paramagnetic. The paramagnetism in the lanthanides ions arises because of the presence of unpaired electrons in their 4f subshell. The ions La3 positive, Lu3 positive, Ce4 positive and Yb2 positive are diamagnetic because they have no unpaired electrons. The magnetic behavior of a substance is expressed in terms of the magnetic moment. The larger the number of unpaired electrons, the higher is the magnetic moment. The magnetic moment arises from two types of motion of the electron. The spinning of electron on its own axis generates a magnetic moment called spin magnetic moment, and orbital motion of the electron around the nucleus also produces magnetic moment called orbital magnetic moment. The magnetic behavior in case of lanthanides arises due to the contribution of both spin magnetic moment as well as orbital magnetic behavior. This behavior of lanthanides is in contrast with the behavior of transition elements of D block, where the magnetic moment corresponds exclusively to spin only values. In case of transition elements, the d orbitals are not well shielded from the environment and interact strongly with the ligand surrounding the metal ion. Because of the electric field of the ligands, the orbital motion of the electron is restricted. That causes the orbital moment to decrease considerably. In other words, the orbital moment of the electrons in case of transition elements can be neglected. On the other hand, in case of F block elements, the 4f subshells are well shielded from the surroundings and do not interact with the surrounding ligands. As a result, the orbital motion of the 4f orbitals is not restricted or quenched. Thus, the magnetic moment of the lanthanide ions arising due to both electron spin and orbital motion of the electron can be calculated from the expression mu is equals to 4s s plus 1 plus l into l plus 1 under the root, where s is equal to total spin quantum number and L is equals to total orbital magnetic quantum number. The simple relationship works only for the lanthanides La plus 3 F0, Gd3 positive F7, Lu3 positive F14. Both La3 positive and Lu3 positive have no unpaired electrons and consequently both have zero magnetic moment values. However, the magnetic properties of the lanthanides are different from those of transition elements. In the lanthanides, the spin contribution S and the orbital contribution L coupled together to give a new quantum number J. The new quantum number J can have two types of values. J is equals to L minus S when the orbital is less than half full. J is equals to L plus S when the orbital is more than half full. Therefore, the magnetic moment values for the lanthanides in Bohr magneton is given by mu is equals to G under the root J into J plus 1, where G is the length splitting factor for the electron and is defined as G is equals to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 upon 2J upon J plus 1 is equals to 1 is equals to 3 by 2 plus S into S plus 1 minus L into L plus 1 upon 2J upon J plus 1. The theoretical and experimental determined magnetic moment values of the tripositive lanthanide ions are given in table 4.4. It is clear from the table 4.4 that there is an excellent agreement between the theoretical and experimental values when the magnetic moments are calculated on the basis of spin and orbital contribution together. All the tripositive lanthanides ions excepting La3 positive and Lu3 positive contain unpaired electrons and are therefore paramagnetic. A plot of the magnetic values of tripositive lanthanide ions reveals that the magnetic moment values increase first up to neodymium and then decrease up to samarium. It increases steadily again and reaches a maximum value for dysprosium ion and then start decreasing till it reaches zero value for lutetium ion, which is diamagnetic. It is important to remark that high values of the magnetic moments for Tb3 positive and Dy3 positive and HO3 positive clearly demonstrate the role of orbital contribute towards the magnetic moment of the later lanthanides. A distinct feature of the curve is its unusual shape. The unusual shape of the curve arises because when the F subshell is less than half filled, the spin and the orbital magnetic moments work in opposition, but when the F subshell is more than half full, they work together. Example 4.1. Calculate the magnetic moment of Gd3 positive ion in Bohr magneton. The electronic configuration for gadolinium is Zd is equals to Xc4f7 5d1 6s2 and that of Gd3 positive is Gd3 positive 54Xc4f7. Thus there are 7 unpaired electrons. The magnetic moment can be calculated using the expression mu is equals to 4s into s plus 1 plus l into l plus 1 under the root m1 plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3 electrons are written. S for Gd3 positive is equals to half into 7, that is 7 by 2. L for Gd3 positive plus 3 plus 2 plus 1 plus 0 minus 1 minus 2 minus 3 is equals to 0. Mu is equals to 7.9 Bohr magneton. Color and spectral properties. Lanthanides in their element state are silvery white, while many lanthanides ions are distinctly colored both in the solid state as well as in the aqueous solution. The color of the lanthanide ion depends primarily on the number of unpaired F electrons. The color of the lanthanide ion remains same even on changing the counter anion. Thus, color of the lanthanide ion is characteristics of the cation. It has been found that lanthanide ion containing NF electrons often have a similar color to those with 14 minus NF electrons. The color of the lanthanide ions can be grouped symmetrically about the trivalent gadolinium ion as shown in table 4.5. The color of the lanthanide ion is due primarily to the absorption of light from the visible region of the spectrum that results in the electronic transition within the 4F level. This type of transition is called FF transition. A unique feature of the spectra of tripositive lanthanide ions is that the absorption bands are sharp line-like bands in the ultraviolet, visible or near infrared region. This behavior is in contrast to the absorption bands of DD type transition metals, which appear as broad absorption bands. The bands of lanthanide ion are so sharp that they are used for characterizing lanthanides. The reason for very sharp absorption band is that the 4F orbitals are located deep inside the atom. Thus, they are effectively shielded from environment factors such as the nature and the number of ligands which form the complexes and from vibrations of the ligands. A typical lanthanide ion spectrum of holmium is shown in figure. Thus, the color of the lanthanide ion does not change with different ligands. In other words, the absorption bands show little dependence on the nature of ligand. It is important to mention here that this behavior is in contrast with the transition element where DD transition give absorption bands whose position changes from ligand to ligand and width of the peak is greatly broadened because of the vibration of the ligands. Vibration of the ligands changes the external field. However, lanthanides in the +2 and +4 oxidation state with the same number of electrons, isoelectronic ions do not have same color as observed in case of lanthanides in the +3 oxidation state. Some of the typical isoelectronic lanthanides in the +2 and +4 are shown in table. Apart from FF transition, sometimes the color of the lanthanide ion can also be attributed to FD transition. The FF absorptions of lanthanides ions have low intensity because these transitions are not allowed. However, FD transitions are allowed. As a result, they show very intense absorption bands. For example, C3 positive and TB3 positive show very intense absorption bands. Transitions due to FD bands are broad, in contrast to narrow FF bands. In addition to FF and FD transitions, the color of some of the lanthanides ion can be due to charge transfer. This transfer of charge occurs from the ligand to the metal. This is more probably if the metal is in high oxidation state or the ligand has strong reducing properties. Charge transfer usually produce intense colors. For example, strong yellow color of C4 positive solutions arises due to charge transfer rather than FF transition. The blood red color of SM2 positive is also due to charge transfer. Ionic radii and lanthanide contraction. Covalent and ionic radii increase on moving down a group in the periodic table. This is due to the presence of additional shells because between the successive periods. On the other hand, on moving from left to right across a period, the covalent and ionic radii decrease. This is attributed to the increased effective nuclear charge as a consequence of which the outermost electrons are attracted more and more. This results in the outermost electrons being pulled more and more closer. We also know that the shielding effect of electrons decrease in the order S, then P, then D, and then F. The atomic and ionic radii of lanthanides are given in table 4.7. A careful inspection of the table 4.7 reveals that as we move along the lanthanide series from lanthanum to lutetium, there is a gradual decrease in the size of the atoms and ions with the increase in atomic number. It has been observed that in case of tripositive lanthanides ions from Ce3 positive to Lu3 positive, the ionic radii decrease from 1.03 Armstrong to 0.86 Armstrong. This shows that overall decrease of 0.17 Armstrong occurs in going from Ce3 positive to Lu3 positive ion. This is indeed a very small decrease in comparison to elements of other groups and periods. The atomic radii of the elemental lanthanides also decrease from 1.83 Armstrong to 1.73. The total decrease of atomic radii from Ce to Lu comes out to be 0.10 Armstrong. This small steady decrease in the atomic or ionic radii of the lanthanide elements with increase in atomic number is called lanthanide contraction. Cause of lanthanide contraction. The shapes of the orbitals account for the relative atomic radii of F block elements. The lanthanides involves the gradual filling of 4f orbitals. The lobes of the 4f orbitals occupy markedly different regions of spaces and are therefore far apart from each other. Consequently, f orbitals repel one another very weakly. Secondly, electrons density in f orbital is low near the nucleus as a result of being away from the nucleus. 4f orbitals are not very effective at shielding other electrons from the nucleus. Thus, with the increase in atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increases. This increases the inward pull of the 4f electrons and result in the reduction of the size of atom of ion. This contraction in the size of atom or ion by pulling the valence electrons inward due to high nuclear charge and the poor shielding effect of the f electron is the main cause of what is called lanthanide contraction. Consequences of lanthanide contraction. Some of the important consequences of lanthanide contraction are given below. Number 1. Steady decrease in size of lanthanide ions. As a result of lanthanide contraction, there is a gradual or steady decrease in the ionic radii of lanthanides. Number 2. Electronegativity. There is a slight increase in the electronegativity of the trivalent ions. Number 3. Electrode potential values. There is a small but regular increase in the electrode potential values E0 for the process. Number 4, resemblance of second and third transition series. The atomic radii of elements of second transition series are typically greater than those in the first transition series. However, the radii of the third transition series elements are about the same size as that of second transition series. This similarly in the atomic radii is due to presence of F block near the beginning of period 6 as shown below in the table. There is a pronounced decrease in the atomic radii along the lanthanides when the d block resume at the lutetium. The atomic radius has fallen from 2.24 Armstrong for barium to 1.72 Armstrong for lanthanum. As a result of this, the atoms of all the following elements are smaller than expected. In brief, as a result of lanthanide contraction, the chemistry of second and third transition series resembles each other more than the elements of first and second transition series. Difficulty in separation. Because of the very small change in the size of lanthanide ions in the lanthanide series, their chemical properties are alike. This causes the separation of elements is a difficult task. Number 7, high density. The lanthanide contraction is responsible for the high density of the elements of third transition series. A block of iridium, for example, contains as many atoms as a block of rhodium of the same volume, but each iridium atom is nearly twice as heavy as each rhodium atom. Therefore, the density of iridium is nearly twice that of rhodium. Difference in basicity. The size of lanthanide ion decreases regularly with the increase in atomic number in the lanthanides. The decrease in the size of the cation tends to increase the covalent character according to Fajan's rule. As a result, the bonding of the smallest cation and the hydroxide ion becomes mostly covalent. In other words, the basic strength of hydroxide decreases. This explains clearly that LaOH thrice is the strongest while LuOH thrice is the weakest base. Similar to hydroxides, there is also a decrease in the basic strength of oxides of lanthanides with increase in the atomic number. The decrease in basic strength of oxide and hydroxide of lanthanides with increasing atomic number is also reflected in several other related properties. For example, number 1, hydrolysis of ions. Due to a decrease in basic strength, there is slight increase in the degree of hydrolysis in solution from La3 positive to Lu3 positive. It means La3 positive ions are less readily hydrolyzed than the Lu3 positive ion. Number 2, solubility of the salts. Hydroxides of lanthanides precipitate with decreasing pH values from the nitrates of La3 positive to Lu3 positive at 20 degrees Celsius. For example, La3 positive precipitate at pH 6.83, whereas Gd3 positive precipitate at pH 6.83, while Lu3 positive precipitate at pH 6.30. Number 3, thermal decomposition of oxysalts. The stability of the trinitrates of the lanthanides decreases with the increase in atomic number. Thus, LaNO3 thrice, which is more basic, decomposes little, whereas LuNO3 thrice decomposes readily. Complex formation tendency of lanthanides. Compared with the transition metals, lanthanides ions do not readily form complexes. It is primarily due to larger size of the ions, which results in the small charge to ionic radius ratio. Lanthanides ions form complex preferably with fluorine and oxygen donor ligands. They form complex with beta diketones such as acetyl acetone, oximes, ethylene diamine tetra acetic acid, and hydroxycarboxylic acid such as citric acid, HOOC, CH2COH, COOH, CH2COOH. Acetyl acetone complex of tripositive lanthanide ion is shown below. In figure 4.5, the lanthanide elements are often 6 coordinated in complexes. However, higher coordination numbers are also known in some complexes. For example, 8 coordination is found in La ACAC whole thrice, H2O twice, which ACAC is equals to acetyl acetonate, as well as in the anionic spaces Y, CF3CO, CHCO, CF3 negative 4. The high charge density on Ce4 positive is expected to form stronger complexes than the tripositive ion. Ce4 positive has been found to form the dianionic complex CeNO3 6 negative in non-aqueous medium N2O4. This is an interesting complex in which the coordination number of cerium is 12. Nitrate ion behaves as bidentate ligand as shown in figure 4.6. Organometallic compounds. Lanthanides ions being highly electropositive do not form complex with pi bonding ligands like CONO. The inability to form complexes is also due to non-availability of F orbitals for bonding. However, lanthanides form 2 types of compounds. Number 1, predominantly ionic cyclopentadienydes. Number 2, sigma bonded alkyls aryls. The cyclopentadienydes can be prepared by the reaction of anhydrides LnCl3 and NaC5H5 in a polar solvent like tetrahydrofuran in appropriate molar ratio. Using this methodology, it is possible to prepare cyclopentadienydes compounds of the type LnC5H5 thrice, LnC5H5 twice Cl, and LnC2H5Cl2. In polar solvents, these complexes are highly solvated and monomeric in nature. However, in polar solvents, the trace compounds, that is LnC5H5 thrice, are insoluble, while the bis compounds LnC5H5 Cl dimerize. The alkyl and aryl lanthanides can be prepared by the mathematical reaction either or in the THF solutions. LnCl3 plus 3RLi gives R3Ln plus 3LiCl. LnCl3 plus 4RLi gives LiR4Ln plus 3LiCl, where R is equals to alkyl or phenyl. The triphenyl lanthanides are polymeric compounds. The first fully characterized compounds was LiTH44 LuC6S3Me2 whole 4, in which the lutetium ion is tetrahedrally coordinated to 4 sigma aryl groups. The methyl derivatives have recently been obtained. 4.9 Occurrence of lanthanides. Lanthanides were originally named as rare earth or rare earth elements because they were believed to be rare. However, the term rare earth is misleading as these are actually fairly common now. The word earth was used because most of these elements occur as oxide, which in early times meant earth, with the exception of promethium, which is radioactive. All the lanthanides occur naturally. Recent studies have revealed that some of the lanthanides, namely cerium, lanthanum, neodymium, occur in fairly abundant quantities. It has been found that lanthanides with odd atomic numbers are less abundant than the lanthanides with even atomic numbers. Cerium has been found to be almost as abundant as copper. All the lanthanides, excepting cerium and promethium, are more abundant than iodine. The abundance of lanthanide elements and the number of naturally occurring isotopes are given in table 4.9. A number of minerals containing lanthanide are also known. Some of important minerals are: number 1, monazite. Monazite sand is the most important and widely spread mineral. It accounts for 78% of the mined lanthanides. It predominantly contains phosphates of the lighter lanthanides with cerium, neodymium, rhasidium, together with small amounts of deuterium and the heavier lanthanides along with thorium phosphate. Monazite has been found to occur in Brazil, USSR, USA, Southern India, and Malaysia. Number 2, bastanesite. Bastanesite is a mixed fluorocarbonate with the formula MCO3F with MEC3 positive, La3 positive, Nd3 positive, and Pr3 positive. Bastanesite differs from monazite sand as it does not contain yttrium and the negligibly small amount of thorium in it. Large deposits of the mineral bastanesites are found in Sweden and New Mexico. Number 3, cerite. The mineral cerite contains double silicates of Ce, La, Pr, Nd, and Sm along with aluminium and iron. Extractions of lanthanides from monazite. The mineral is crushed to obtain fine powder. It is digested with the concentrated sulfuric acid till a paste of lanthanide sulfate is obtained. The paste is separated by centrifugation and treated with cold water. When silica, being insoluble, is separated out, the solution containing soluble sulfates is neutralized with ammonium hydroxide. When thorium, zirconium, titanium are precipitated as the respective phosphates, the resulting filtrates treated with sodium phosphate. This treatment separates the lanthanide elements into two groups of lighter lanthanides are precipitated out as double sulfates, while the heavier lanthanides remain insoluble as simple sulfates. The precipitated double sulfates of heavier elements are treated with the concentrated solution of sodium hydroxide, wherein these are converted into the mixture of the corresponding oxide and hydroxides. The mixture is subjected to washing to remove sodium sulfate formed during the course of the process and allowed to dry in air at 100 degrees Celsius. During this workup, cerium gets completely oxidized to cerium 4 oxide CeO2, whereas the other lanthanides are converted in the sesquic oxide Ln2O3. The resulting mixture of these oxides is treated with dilute nitric acid, and all the oxides except CeO2 dissolves to form the corresponding nitrates. CeO2 being insoluble in dilute HNO3 is separated out. This crude sample of CO2 is dissolved in concentrated HNO3. Addition of dilute sulfuric acid precipitates out cerium as basic nitrate of the formula COHNO3 3 which is a red crystalline solid. The various steps involved in the separation of cerium are outlined systematically in the flow sheet diagram 4.7. After the successful separation of cerium, the other lanthanides are separated into individual elements by employing different methods based primarily on the principle of varying solubilities. Methods of separation into individual components. The properties of metal ions are governed by the size and charge of the ion. Since all lanthanides ions are nearly of the same size and invariably carry +3 charge, they have almost similar properties. As a result, the separation of lanthanides from one another is extremely difficult. A number of methods have recently been developed based upon the repeated fractional crystallization, fractional precipitation, ion exchange methods, etc. for the separation of lanthanides. The conventional methods of separation take advantage of the slight differences in basic properties, solubility or stability. However, recently ion exchange method has been found to be the simplest. Some of the methods are discussed below. Precipitation. With a small amount of the precipitating agent, a substance with the lowest solubility is precipitated out first. Suppose hydroxyl ions OH negative are added to a small containing a mixture of lanthanide nitrates LnNO3 thrice the weakest base LuOH3, which has the lowest solubility product is precipitated first, and the strongest base LuOH thrice, which has the highest solubility product is precipitated last. The process, when repeated several times, helps in the complete separation of lanthanides. Number 2. Fractional crystallization. Simple salts of lanthanides such as nitrates, oxalates, sulfates, perchlorate, etc. together with the double salts such as 2-LnNO3, 3-MgNO3, 2,24H2O form well-defined crystals. The solubility of these salts decreases from La to Lu. As a result, salts at the end of the series, example lutetium salts, which have low solubility, will crystallize out first. Similarly, salts at the first start of the series, say lanthanum salts, which are most probable, will crystalline out in the end. The process requires repeated crystallizations to get good separation. This is laborious method of separation is not preferred these days. Number 3. Solvent extraction. This method of separation is based upon the fact that the solubility of lanthanide nitrates in aqueous and organic solvents like tributyl phosphates is different. In the solvent extraction process, a dilute aqueous nitric acid solution of the lanthanides is extracted by means of a counterflowing solution in tributyl phosphate in kerosene. Thus, in the extraction from aqueous nitric acid solution by tributyl phosphate, and equilibrium is established. The extent of extraction increases with the decrease in ionic radius. In other words, the cations of elements with higher atomic numbers are extracted first. Using this method, a high degree of separation is achieved. Number 4. Complex formation. Complexing agents like ethylene diamine tetraacetic acid are well known to form complexes with lanthanide ions. The stability of these complexes increases with decreasing size of lanthanide ion. Thus, lutetium ion Lu3 positive complex of EDTA is the most stable of all the complexes of lanthanides with EDTA. If some acid is added to the solution of these complexes with EDTA, the least stable EDTA complex will dissociate and release the lanthanide ion. Addition of oxalic acid will immediately precipitate out the free lanthanide ion, preferably at the left hand side of the series, that is CH3 positive, Br3 positive, Na3 positive, which are weakly complexed with EDTA. Oxalate of the lanthanides are insoluble in water. However, addition of the oxalate ions to EDTA complex lanthanide ions will not precipitate the lanthanide ions as they are already complexed with EDTA. Number 4. Change in oxidation state. Most of lanthanide exhibit an oxidation state of +3 in its compounds, whereas a few lanthanides show the oxidation state +2 and +4 in its compound. As a result, the lanthanides with +3 oxidation state have properties altogether different from lanthanides with +2 and +4 oxidation state. This difference in the properties in different oxidation states is extremely useful in the separation of lanthanides. Cerium can be separated from the mixture of lanthanides easily because it is the only lanthanide which has +4 oxidation state in aqueous solution. Thus, if alkaline KMnO4 is added to the mixture of lanthanides, it is only the cerium which will be oxidized to +4 oxidation state on account of high charge. Ce4 positive is the smallest and less basic than Ce3 positive or any other lanthanide in +3 oxidation state and consequently is less soluble. It can be separated by precipitating it as CeOH4 by the addition of NaOH, leaving behind the other trivalent ions in solution. Similarly, europium can be separated from the rest of the lanthanides because europium is the only lanthanide which is stable in +2 oxidation state. Addition of zinc amalgam, a reducing agent, to the mixture of lanthanide ions only reduces EU3 positive to EU2 positive, leaving the other lanthanides in the +3 oxidation states. If H2SO4 is added at these states, EU2 positive is only precipitated as europium sulfate EuSO4, while the sulfates of all the other lanthanides ions remains in solution as Ln2SO4 thrice. It is important to mention that SM2 positive and Yb2 positive can also be separated by reducing with zinc amalgam. However, these get oxidized slowly by water like europium. Number 6. Ion exchange method. Ion exchange method is one of the most convenient and efficient method for the separation and purification of the lanthanides. In this method, a solution of lanthanide ions is passed through a column of synthetic ion exchange resin which contains the functional group COOH or SO3H. Lanthanides ions, when come in contact with the resin containing the acidic functional group, undergo proton exchange as Ln3 positive plus 3H resin is in equilibrium with Ln resin 3 plus 3H positive aqueous. In the process, the lanthanide ions are bonded to the resin and H positive ions are produced or washed through the column. The bonding of the lanthanide ions to the resin depends on the size of lanthanide ion. Since lanthanide ions are present in aqueous solution, these are heavily hydrated. The smaller the lanthanide ion, the most heavily hydrated it is. Thus, lutetium ion Lu3 positive, which is the smallest in size, is the most heavily hydrated one. It means that the size of hydrated lutetium ion is maximum. It means that the smaller sized hydrated lanthanide ion binds strongly with the resin and large sized lanthanides ion binds loosely with the resin. The bonded metals ions are diluted and which is washed of the column by a complexing agent. The commonly used complexing agent is a buffered solution of citric acid, ammonium citrate at pH is equals to 8. During elution, the ammonium ions elutes the metal ions from the resin as Ln resin 3 plus 3 NH4 positive gives 3 NH4 resin plus Ln3 positive aqueous. The metal ions in turn then form a complex by combining with the citrate ion. Ln3 positive plus citrate gives Ln citrate complex. As already discussed, hydrated lutetium ion, being the largest size ion, will bind less firmly to the resin. It therefore will be eluted first. On the other hand, hydrated lanthanum ion, being the smallest size hydrated ion, will bind strongly to the resin. Therefore, it will be eluted in the last of all. Using ion exchange method, it is possible to separate all the trivalent lanthanides ion based upon the strength to which these are bonded with the resin, which in turn depends upon the size of hydrated lanthanide ion. In brief, the heavier lanthanide elements will be eluted, the column first, followed by the less heavier elements, and finally by the highest lanthanide element. Elution curve of the lanthanide elements form an ion exchange resin column is shown in figure 4.8. Production of lanthanide elements. We have listed in the preceding section a number of methods for the separation of closely related lanthanides. In this section, we shall illustrate methods for the production of the elements. Some of the commonly used methods for the production of lanthanide metals are discussed below. Number 1. Electrolysis of fused chlorides. A mixture of lanthanide chloride LnCl3 is fused with NaCl or CaCl2 and electrolyzed in a graphite lined steel cell which serves as the cathode and a graphite rod as the anode. This process is mainly used for lighter low melting C and for Sm and Eu. Number 2. Reduction of anhydrous chloride with sodium. Lighter lanthanides such as La, C and Gd are prepared by the reduction of the corresponding trichlorides with elemental sodium at 1000 degrees Celsius. LnCl3 plus 3 Na at 1000 degrees Celsius, Ln plus 3 NaCl. Number 3. Reduction of anhydrous trifluorides with calcium or magnesium. Heavier lanthanides are produced by the reduction of anhydrous trifluorides with elemental Calcium anhydrous trifluorides are preferred because they are non-hygroscopic and less volatile than the trichlorides, and secondly, the resulting CF2 produced is stable. 2 LuF3 plus 3 Ca at 1000 degrees Celsius gives Lu plus 3 CaF2. Compounds of lanthanides. All the lanthanides are soft and silvery white metals. They are highly electropositive and are therefore very reactive. The heavier lanthanides are less reactive than the lighter lanthanides because they form a protective layer of oxide on their surface. Most of the lanthanides form compounds in the +3 oxidation state. However, small compounds of lanthanides in the +2 and +4 oxidation state are also well known. Let us first of all discuss the compound of lanthanide in the +3 oxidation state. Compounds in +3 oxidation state. Lanthanide oxides Ln2O3. All the lanthanum metals tarnish readily in air. These burn in oxygen, forming the corresponding Ln2O3. The oxides can also be prepared conventionally, either by heating the carbonates or by decomposing the corresponding nitrates. 4Ln plus 3O2 gives 2Ln2O3. Ln2CO3 thrice gives Ln2O3 plus 3CO2. 4 NO3 thrice gives 2Ln2O3 plus 2NO2 plus 3O2. Lanthanide oxides are known to absorb water and carbon dioxide from the air to form the hydroxides and the carbonates respectively. As a result, these are basic in nature. The basic characteristics of the oxides decreases with the increase in atomic number of the lanthanides. This is due to the lanthanides contraction, whereas in the size of lanthanides decrease from La3 positive to Lu3 positive. La2O3 is strongly basic, whereas Lu2O3 is a weak base. Lanthanide hydroxides. The lanthanides are very reactive metals. These react slowly with cold water but more rapidly on boiling with the liberation of hydrogen to form the corresponding hydroxides. 2Ln plus 6H2O gives 2LnOH thrice plus 3H2. The hydroxides can also be prepared by adding dilute solution of sodium hydroxide to a solution of containing Ln3 positive ions. Ln3 positive plus 3OH negatives gives LnOH3. The hydroxides are precipitated in the form of gelatinous precipitates. These hydroxides are ionic and basic. Lanthanides hydroxides are less basic than CaOH twice but more basic than AlOH thrice, which is amphoteric. The basic character decreases with the increase in atomic number along the series. Thus, LOH3 is most basic, whereas LOH3 is least basic. Lanthanide halides LNX3. Lanthanides trifluoride are obtained by the reaction of HF or NAF with the solution containing the lanthanide ion Ln3 positive. Ln3 positive plus 3F negatives gives LnF3. Lanthanide fluorides are important because of their insolubility. However, fluorides of heavier lanthanides are slightly soluble in excess of HF due to complex formation. Anhydrous lanthanides chlorides are prepared by heating the metal in an atmosphere of chlorine or by heating the oxide with phosgene carbonyl chloride. 2Ln plus 3Cl2 gives 2LnCl3. Hydrated chlorides can be conventionally prepared by heating the oxides with appropriate ammonium halide. Ln2O3 plus 6NH4Cl at 300 degrees Celsius gives 2LnCl3 plus 6NH3 plus 3H2O. The chlorides are non-volatile deliquescent solids. They are soluble in water and crystallize with 6 or 7 molecules of water of crystallization LnX3, XH2, X is equals to 6 or 7. Hydrated trichlorides can also be prepared by dissolving the oxides or carbonates in hydrochloric acid. Ln2O3 plus 6HCl gives 2LnCl plus 3H2. The anhydrides, lanthanides, trichlorides cannot be prepared by simply heating the hydrated lanthanide trichloride. In fact, on heating, the hydrated trichlorides are converted to oxychlorides. LnCl3 6H2O on heating gives LnOCl plus 5H2O plus 2HCl. Anhydrous lanthanide tribromides and triiodides are prepared by the direct combination of the elements. 2Ln plus 3X2 gives 2LnX3. X is equals to Br or I. The tribromides and tribromides are more susceptible to hydrolysis and are generally contaminated with oxyhalides. Lanthanide nitrides. At high temperature, the lanthanides react with nitrogen to give nitride of the formula LNN. It gets hydrolyzed by water like AIN to give the corresponding hydroxide with the liberation of ammonium. LN plus H2O gives LNOS thrice plus NH3. Oxosalts of lanthanides. A large number of oxosalts of lanthanides are known. These include nitrates, carbonates, sulfates, oxalates, phosphates, and perchlorates. These are generally prepared by dissolving the lanthanide oxide, hydroxide, or carbonate in the corresponding acid. For example, Ln2O3 plus 3HNO3 gives LnNO3 thrice plus 3H2O. The resulting solutions are cooled when crystals of hydrated oxosalts are obtained. Double salts of lanthanides. It is important to note that lanthanide sulfates are known to form double salts with ammonium and alkali metal sulfates of the composition. NH4 2SO4 dot Ln2SO4 3 dot 8H2O. Na2SO4 dot Ln2SO4 thrice 8H2O. The double salts in case of Lm are generally associated with 24 water molecules of crystallization.